All right, so welcome everybody and welcome back everybody, because we are back, second year of the IITE Theoretical Ecology Seminar Series, and it is my great pleasure to welcome Jacob O'Sullivan from Queen Mary University of London, who is going to be presenting us some emergent properties of macroecological Lotka-Volterra models. So without further ado, the floor is yours. Please, unless you are Jacob, mute your microphones. Thank you very much.
Okay, thank you. Can you just confirm that you can hear me and that you can see my presentation?
Yes.
Okay, great. All right, so yes, good afternoon. Some of you, I guess it's good morning. I'm Jack O'Sullivan. And first of all, let me say thank you for the invitation and thank you all for coming. And again, welcome to another semester of the IITE seminar series. I'm here today representing the Queen Mary Theoretical Ecology Group. So that's myself, Chris Terry and Axel Rosberg. And I'm going to talk to you today about the emergent properties of Lotka-Volterra metacommunities, specifically the emergent macroecological properties of these systems. So just as a quick motivation before I begin the talk, this slide is intended to give you a holistic idea of what we hope to achieve with our models. So we are interested in how local processes propagate up the organizational hierarchy and drive regional patterns in biodiversity. Okay, and I like to use this sand pile model as an analogy here. So in this sand pile model, grains of sand are introduced one by one, assembling the sand pile. And after each introduction, the microscopic interactions between the grains of sand are simulated. And these basically just involve the exchange of spatial position and gravitational potential energy between the grains. Now, eventually, as you might expect, the pile converges on a robust macroscopic structure. So that involves its volume, the angle between the sides and the base. And this robust structure persists despite continued arrival of new grains. Okay, at this stage, then, the assembly of the macroscopic structure can be said to be intrinsically constrained by the onset of what's called self-organized criticality. Okay, so essentially we have the microscopic interactions between the grains of sand which propagate up and drive the macroscopic structure of the assemblage. In the meta-community case, we are interested in how ecological processes influence regional patterns, and whether there exists an analogous critical state which ultimately drives and regulates the macroecology of the meta-community. I'm getting a bit of noise through.
Please, as I said, turn
off
you're the microphones if you are not Jacob Sullivan. I will actually forcefully do that. Okay, thank you.
Thank you.
All good.
Okay, good. So just to give you an idea of where I'm going with this talk, I'm going to begin with a discussion of structural instability in ecological models and how it regulates key biodiversity properties such as species richness. I'll then briefly describe some empirical evidence of diversity regulation in nature. Then I'll give you a quick introduction to the Lotka-Volterra metacommunity model before describing the intrinsic regulation of biodiversity at both the local and regional scales that we observe in these models, as well as a handful of emergent properties, macroecological properties, that we observe when these models are allowed to self-organize. Okay, so let's start with a brief discussion of the process which regulates biodiversity in the zero-dimensional Lotka-Volterra, and I mean zero-dimensional in the spatial sense. Okay, so we're dealing with a point community. So equation 1 is the probably very familiar Lotka-Volterra competition model. B here is a vector of biomasses, and this equation describes the time evolution of that vector, with R a vector of intrinsic growth rates, which in some sense reflects the underlying abiotic or environmental distribution. And A is an interaction matrix describing the impact of species on one another's growth rates. If we assume that this system converges on a fixed point, and we make the further assumption that all species are extant, that is that BI is greater than 0 for all species, then we can precisely predict the distribution of biomass, the equilibrium biomass vector for this community model, okay? And it is given by the inverse of the interaction matrix A multiplied by the growth rate vector R. And let's note at this point that the inversion of the interaction matrix A has profound consequences. Why is that? Well, if one or more of the eigenvalues of the interaction matrix A is precisely equal to 0, then its inverse will be undefined. And as a result, the equilibrium biomass distribution will have no finite solution. Okay, so it's straightforward to show then that there is some strict limit on this interaction matrix. It cannot have an eigenvalue precisely equal to 0. And further, again, as a result of this inversion, the solution B star depends sensitively on model parameters when the eigenvalues of A approach 0. Okay, such that small perturbations in either A or R can lead to relatively large shifts in the system state. It's sometimes referred to as an ill-conditioned or ill-posed problem. Okay, so let's ask now, in what circumstances do we expect the eigenvalues of this interaction matrix A to approach the origin? So let's assume that A can be modeled as a random matrix. And for simplicity in this discussion, let's assume that the mean of the interspecific interaction coefficients is 0. When this is not the case, there are additional terms to consider, but the outcomes of the discussion is the same. And let's also assume that the diagonal of the interaction matrix is a vector of 1s. In other words, that we're dealing with a normalized interaction matrix. In this case, then, the eigenvalue spectrum of the interaction matrix A will form a circular cloud centered on 1 and with a radius given by this expression here, which depends on the square root of S, the species richness within our model. Okay, so as you increase the species richness of your interaction matrix, of your community model, you drive the leading eigenvalue towards the origin, towards that scenario in which there is no finite solution to the equilibrium biomass distribution. So from this very simple analysis then, it's possible to show that there is some fundamental limit on the number of species that can coexist within an ecological community. And further, we can predict the species richness at which this community will have no finite solution to the equilibrium biomass distribution. So earlier I mentioned that as the eigenvalues of A approach the origin, the equilibrium biomass distribution begins to respond sensitively to perturbations in the model objects. Okay, this sensitivity we term ecological structural instability. And when an ecological model becomes structurally unstable in this sense, small perturbations such as might occur due to abiotic fluctuations manifest through the vector R, or through changes in the interaction network, such as occur in the context of ecological invasions, lead to disproportionate changes in the system state, up to and including the loss of species. So then in the context of community assembly, we eventually arrive at a scenario in which the average number of species losses following ecological invasions is 1. And in this context then, the community has become saturated with respect to diversity. Each new arrival is likely to produce the loss of 1 or more residents. So what I've just described leans very heavily on the phenomenology of random matrices, and so is in a sense pseudo-mechanistic. There is a more mechanistic analysis available. I won't go through that in detail, but I will show you one key result from that analysis, and that is this equation here, which predicts not that limit at which there is no finite solution to the equilibrium biomass distribution, but instead the actual species richness at which we expect such an ecological community model to saturate. Okay, and that's given here as a function of the mean of the interspecific interaction coefficients and their variance only. Okay, so we can think of these microscopic pairwise interactions propagating up the organizational hierarchy and ultimately determining the macroscopic structure of this community model, specifically the number of species. Right, as a brief aside, it's important to note that structural instability and its opposite, sometimes called robust coexistence, has been studied from other perspectives. For example, here as a mechanism limiting similarity in ecological communities. Here as a process by which, or driving the systematic selection of particular network structures, in this case in mutualistic networks. And also here the authors study how structural instability interacts with abiotic fluctuations to determine the range of environmental conditions within which a community can sustain without the loss of species. So each of these approaches shares a common theoretical underpinning. We study this phenomenon from the perspective of community assembly. Okay, so we ask how the onset of this structurally unstable paradigm regulates community assembly processes. Okay, so I've just gone through that in an abstract analysis. Let's look at how this intrinsic diversity regulation plays out in a community assembly model. Okay, the way that these models work is that at each iteration of the assembly algorithm, I'm going to randomly generate and introduce a new species into the community and then simulate the population dynamics using the standard Lotka-Volterra competition model. Any species whose biomass drops below some low numerical threshold is considered extinct and removed from the system. So in the leftmost panel, you see that the number of species in the model initially increases linearly as a function of the invasion event, but eventually reaches some stochastic asymptote, as you can see emerging now. In the central panel, you see a heat map representation of the interaction matrix, and you can see that this matrix is changing. Okay, we have turnover in this system. And then in the right panel, you see the spectrum of that interaction matrix, which conforms to our expectation. We have the leading eigenvalue of the interaction matrix approaching the origin. And when it approaches the origin, the system becomes highly sensitive to perturbation and converges on some diversity equilibrium. Okay, so we've gone from, if you like, an analytic prediction of intrinsic diversity regulation to demonstrating it in a simple community assembly model. But let's now ask a very important question, whether or not this seems like a biologically plausible scenario. So if ecological communities in nature are actually subject to this kind of intrinsic regulation, or in contrast, if the combined effects of environmental and demographic stochasticity ultimately limit species richness in real ecosystems to such an extent that these theoretically predicted diversity limits simply never play out, they never occur in nature. So let's have a brief look then at some empirical evidence in favor of the realism of this intrinsic diversity regulation paradigm. Okay, so here we have a handful of time series which appear to show communities in which, so in the top left, top right, and bottom left figures, the central line represents the observed species richness in these communities. We have desert rodents, breeding birds, and trees inferred from the pollen record in sediment cores. And the upper line represents the cumulative arrival of novel taxa, the lower line, the cumulative losses of taxa from the community. And you'll see that the arrivals and losses are tightly correlated, and as such, we find stationarity in the species richness as a function of time. Okay, in the bottom panel, the black line here represents the observed mammalian diversity based on analysis of the fossil record. Okay, so this is paleoecological data. And the gray lines represent simulated time series, assuming the absence of any intrinsic constraint. Okay, so these are essentially just random walks. And you can clearly see that there's a qualitative difference between the simulations and the observations. And here the author concludes that there must be some intrinsic constraint on the number of species within the record, and also by extension on the diversification of novel taxa. Now, of course, it's very difficult to speculate on what might be responsible for this time invariance in the paleoecological data. Okay, there's the possibility of a wide number of different statistical artifacts at play here, but it is informative to note that there is apparently some time invariance in these key biodiversity properties that can be observed at these very long time scales. Okay, now taking a meta-analytic approach, these authors combined a database of time series. Each point in this map represents a survey site, and the colors represent roughly the biome, so the habitat type. So in figure A underneath, the points on this graph represent the slope of the regression of species richness against time, most of which show no significant trend, okay? And that's indicated by the gray color. They do observe significant trends in some of the time series, but these slopes are symmetrically distributed around 0. So in the author's words, then they find no systematic evidence of a change in species richness over time, and most of the time they observe no trend at all. On the right, they are plotting the slope of the Jacquard similarity as a function of time, and you can see that this is clearly biased towards the negative. So we have apparent stationarity with respect to the number of species, despite continuous turnover in the identity of those species. It's important to note now that the mechanism responsible for this apparent intrinsic regulation of biodiversity is poorly understood empirically. Okay, so it is well understood how intrinsic regulation of biodiversity operates in these zero-dimensional Lotka-Volterra models, these non-spatial models. But until we began this project, it was not known how this structurally unstable regulation might operate in the spatially explicit case, the case in which community composition arises as a result of a combination of abiotic and biotic filtering and dispersal limitation. In other words, it was not known how this process might play out in a meta-community. So these two questions then can be seen as a detailed motivation for the remainder of this talk. First of all, we would like to shed light on whether the analytic insights gained from the analysis of these zero-dimensional models can inform the spatially structured case. Okay? In other words, if these insights are, in a sense, foundational to the more complex models, and if so, then does this indicate the existence of a hierarchical theory of ecology, capable of describing and predicting properties at multiple spatial scales, but with an appropriate reframing? And I'll come back to that idea of reframing in a moment. But we also want to know what are the emergent properties of these metacommunities that are not predicted by the zero-dimension analysis, okay, that by definition are not predicted. And in particular, we want to know if those emergent properties coincide with empirical observations. Okay, so the first step to answering these questions is to build such a metacommunity model. And our approach is as follows. We begin with an underlying abiotic distribution, which we model by sampling points in space from a spatially autocorrelated random field. Okay, the autocorrelation length of this distribution can be tuned, and by varying the length, we can ask useful questions about how emergent diversity structures respond to different levels of environmental heterogeneity. From this abiotic distribution, we then define a species distribution in intrinsic growth rates using a simple quadratic environmental response function. I'm not going to go into details about this function. We can do at the end if you want. I'm just going to note that we have this parameter W, which controls the abiotic niche width, and we keep this abiotic niche width fixed for all species in the metacommunity. Okay, it varies between metacommunities, but we assume neutrality with respect to the niche width. We then generate a spatial network, for example, by sampling these coordinates of our local sites, and then we link those coordinates with some adjacency. Okay, so here I'm showing a Gabriel graph, which is one that we commonly use to define the connectivity of our model landscapes. So dispersal between connected sites is then modeled using a exponential dispersal kernel. So the rate of immigration between sites decays exponentially as a function of distance between those sites. Again, we have a parameter L here, which controls the dispersal length. And again, this is fixed for all species within a given metacommunity. These are simplifying assumptions. And then, of course, we have a network of ecological interactions, which describes the local interactions within the community. And these interactions are randomly sampled. So based on our numerical and somewhat analytic understanding of these systems, the precise details of that distribution do not affect the emergent properties. It is their mean and variance that matters. So we've tried a few distributions, but it doesn't really make that much difference. And then we have some system of equations. So this here is the Lotka-Volterra metacommunity model. And as you can see, at its heart, it is just a simple Lotka-Volterra competition model, but with the addition of terms. Okay, so B is now a matrix, a species by site biomass table. R is a matrix of spatially explicit intrinsic growth rates. A, the local interaction matrix. And then we have this matrix D, which describes the rate of immigration and emigration from each of our sites. And just as in the zero-dimensional case I showed earlier, we use an assembly algorithm to allow this system to self-organize. Now, in order to test the zero-dimensional predictions, we ultimately need an S by S interaction matrix, okay, which is essentially a zero-dimensional approximation to the spatially explicit metacommunity. Okay, we need an interaction matrix that accounts for the intrinsic spatial structure of the metacommunity. And we acquire this regional scale interaction matrix using a computational harvesting experiment. So each species in turn is weakly perturbed away from its equilibrium, and then we record and sum the impact on all other species that results. So in this graphic, I'm just representing the difference between the harvested equilibrium and the non-harvested equilibrium, which we then use to define the regional scale interaction matrix C. So for more details on this method, please see the material that we have published on this already. Okay, so let's look at another of these assembly videos, this time a metacommunity assembly. So unlike the previous case, the central figure now represents this regional scale interaction matrix, right? The zero-dimensional approximation to the metacommunity system, accounting for its intrinsic spatial structure. So on the left, again, we have the regional diversity in black and the average local species richness in gray. And you can see that initially these increase and eventually they will reach, each of them reaches some intrinsic limit. Okay, so typically the local species richness on average will converge prior to the metacommunity scale diversity, the gamma diversity. Okay, so here you see the regional scale interaction matrix and its spectrum. And the key thing to note in the spectrum is that just as in the zero-dimensional case, the regional diversity will saturate at the point at which the leading eigenvalue of this regional interaction matrix approaches the origin. Note that occasionally you will see some flashes in this regional interaction matrix heat map, and very occasionally you might see some negative eigenvalues popping out in this spectrum here. The method that we use to estimate this regional scale interaction matrix is approximate and does sometimes fall prey to numerical errors. Okay, but in general, it appears as if our expectation based on the zero-dimensional analysis similarly applies to the metacommunity case, so long as you take the appropriately scaled interaction matrix. Okay, so that's a qualitative demonstration. Here I show a quantitative demonstration. So earlier I showed this equation which predicts the emergent diversity of a zero-dimensional Lotka-Volterra community under community assembly. If I now replace the mean and variance of the local interaction matrix with the mean and variance of the regional interaction matrix, this equation will predict the gamma diversity of our model metacommunities. Okay, so on the first question then, do the predictions derived from the analysis of the zero-dimensional case help us to understand the emergent properties of the spatial case? This does indeed appear to be true. assuming you take the appropriately scaled interaction matrix. So in this figure now, I'm showing the spectrum of the local interaction matrix A in gray and the regional interaction matrix C in black. Now, remember the regional scale interaction matrix accounts for the combined effects of abiotic and biotic filtering, which drive a non-uniform structure, spatial structure within the metacommunity. And so it more accurately represents the structure of this metacommunity. Okay, maybe we can come back to that later. Okay, so let's move on now to consider some of the emergent properties of the metacommunity models that are not predicted by analysis of the zero-dimensional case.
I'm so sorry to interject. There's constant noise in the background. I'm hearing that somebody sees that some people are not muted. I see on my end for some reason that everybody's muted, but apparently not. Please mute your microphones. Thank you. Sorry.
Thank you.
Back to you.
Okay, yeah, so let's now consider some of the emergent properties of these systems that by definition are not predicted by the zero-dimensional analysis. First of all, let's look at the site occupancy distribution, sometimes called the occupancy frequency distribution, and a related pattern, the range size distribution. Okay, so this figure here represents the spatial network and the underlying abiotic distribution for a model metacommunity. The color here represents the local value of that environmental variable. And you can see that it's quite strongly spatially also correlated. Okay, so following metacommunity assembly, as I showed in the previous video, we end up with some distribution in the spatial structure of the metacommunity. So each of these networks now, and I've removed the edges just for visual clarity, each of these networks represents the spatial distribution of a single species. Okay, so the color corresponds to the local biomass of these species. And you can see that each species has a rather different spatial structure. Okay, one occupying a single site and others occupying more sites, more broadly distributed throughout the landscape. Okay, so we're interested in the distribution of range sizes. Okay, and also the distribution of site occupancy, where site occupancy entails the number of sites where a species is numerically present. Okay, another video now. So in the left panel, again, we have the richness plotted against the invasion event. In the central panel, I'm showing the distribution of range sizes, and in the rightmost panel, the site occupancy distribution. Okay, so at the early stage of the assembly, you have broadly distributed species occupying most of the sites, up to 100, and you also have species with a more narrow distribution. Okay, but the distribution in site occupancy is largely uniform. As we continue the assembly and we drive this metacommunity beyond the local limits, we begin to see a collapse in this spatial structure. Okay, this is essentially a regionalization process through which the average species range size decreases with an associated increase in the between site compositional dissimilarity. Okay, and this is quite a long video, so if I just skip through it, once we arrive at that regional diversity maximum, you can see that we have this strongly right skewed site occupancy distribution and range size distribution. Okay, so in the two figures at the lower part of this slide, okay, I'm taking the identical metacommunity shown before and spontaneously switching off all of the interspecific interactions and then allowing the metacommunity to converge on some new equilibrium biomass distribution. And not surprisingly, there is a radical difference between the spatial structure in the absence of local interactions, okay, and ultimately in the absence of local limits on species richness. So by comparison between the upper two figures corresponding to the case in which we have local limits on diversity and the lower case in which local diversity is unlimited, we can say that those local limits on diversity propagate up the organizational hierarchy and ultimately determine the spatial structure of the metacommunity. Okay, so let's ask now, which of these spatial structures, the upper two panels or the lower two panels, is more biologically realistic? So these data are taken from a seminal paper by Kevin Gaston and colleagues, and it records the range size distributions of 10 large taxonomic groups throughout the UK. Okay, so we have from liverworts to mammals, their British distributions. Okay, and each of these high-level taxa in the UK show a clear right-skewed distribution in their range sizes. And so based on our inspection of the Lotka-Volterra metacommunities, I am tempted then to argue that this observed right-skewed distribution in range sizes is indicative of local ecological processes propagating up to the regional scale, that there is some link between the local and the regional scales for these taxa. Okay, I say I'm tempted because I can think of alternative mechanisms that might drive this right-skewed distribution. For example, if there are some evolutionary constraints on niche widths or dispersal ability. Okay, remember that we assume that niche widths are uniform, are identical for all species, and likewise with dispersal ability. So if in the empirical case, the majority of species have narrow niches and are poor dispersers, this might explain the emergent right skew. Okay, I don't know if that sounds biologically plausible. Okay, I'm not an evolutionary biologist, and I don't know if such an evolutionary constraint could exist, but from my perspective, it feels like the local ecological limit is a more parsimonious explanation for this right skew, but perhaps we can discuss that afterwards. Okay, so moving on to the next emergent property, this is the species area relation. Okay, and we study this by systematically increasing the number of sites and the total area of the model, and then comparing the emergent regional diversity along that gradient in total area. And when we do so, we find a sublinear increase in regional diversity as a function of area. And here I'm showing that in the top panel on double logarithmic axes, we have approximate linearity. So we seem to get a power law increase in richness with area. And then in the lower panel, I'm varying the environmental heterogeneity. So the blue color is the most heterogeneous environment, and the red color is the least heterogeneous environment. And under variation of the degree of environmental heterogeneity, we find variation in the exponents of this species area relation, which range here from 0.2 up to 0.9. On the left then, I'm showing the outcome of an empirical meta-analysis. So this is an analysis of 700 or 800 empirical species area relations fit with a power law, and the exponents of these species area relations fall within the range from somewhere between 0.2 and 0.4. Okay, the color here corresponds to the way in which the species area relation is studied. It's a technical detail, and they decompose their results by terrestrial and aquatic communities here. Okay, so coincident with that sublinear increase in diversity with area, we find a power law decay in the average interaction strength estimated using the harvesting experiment. So in this top figure here, which I call the competition area relation, I'm showing how the average intraspecific interaction coefficients decay according to a power law with area, and likewise the average interspecific interaction coefficients. Interestingly, the intraspecific, the self-interaction terms, decay at a rate which appears to depend sensitively on the heterogeneity, on the abiotic niche width, whereas in contrast, the interspecific interaction coefficients appear to be insensitive to that abiotic niche width parameter. Okay, the precise mechanism driving the area dependence of these average interactions is something that we are still exploring, but it's important to note that we find linear relationships between the exponent of the competition area relation and the species area relation. Okay, and likewise we find linear relationships between the exponents of both of these functions and the abiotic niche width. Okay, and these linear relationships give us good reason to believe that there is some key mechanistic relationship between the decay in the average interaction strength with area and the accumulation of diversity with area, the species area relation. So once again, then we find that the local interactions, and specifically their dependence on total area, can be understood to propagate up the organizational hierarchy and ultimately determine the macroecology at the regional scale. Okay, so the last emergent property of these Lotka-Volterra metacommunities I'd like to show you is the spontaneous emergence of steady state dynamics in spatially and taxonomically large metacommunities, which contrasts to the zero-dimensional case in which the analogously constructed models converge on fixed points. Okay, so let's have a look at some of these steady state dynamics. In each of these videos, the color represents the local biomass of a single species, okay? And the color is a logarithmic color scale. So in a metacommunity of 32 sites, then, this particular metapopulation has a core range in the upper left where it is effectively, its biomass is effectively time invariant, but in the extremes of its range, we can see that it is fluctuating in and out of occupancy. If we double the size of this metacommunity, once again, this particular species occupies the lower left portion of this metacommunity at approximately all times, but even in those sites where it is approximately always present, its local biomass fluctuates by orders of magnitude. And finally, if we double again, here we have 128 sites, and this particular metapopulation is effectively roaming freely throughout the landscape. Okay, so we no longer have a useful decomposition of this range into core and satellite components. Instead, it only ever occupies local communities temporarily. And note that this autonomous fluctuation occurs in the absence of abiotic change and also in the absence of regional invasions. Okay, so this is a long time since the last invasion of a new species into the metacommunity. So these local populations at the community scale drive compositional turnover. And here I'm showing how the rate of turnover increases as a function of the total metacommunity area and accordingly as a function of the total metacommunity richness. I'm using a slightly odd metric to compute the turnover rate here. Okay, so on the y-axis, we have the number of compositional clusters detected in a time series of fixed length. Okay, there is a reason why I choose this slightly odd metric, but I won't go into that today. It relates to a qualitative description of this turnover that you can see in the published material. Okay, so again, without going into great detail, in this figure, I'm showing that there is a key mechanistic relationship between the emergence of this autonomous turnover and local ecological limits to diversity, which, as we've seen, occurred due to the onset of this intrinsic limit, this structurally unstable limit. So to see that then, in the first figure, this is again the species richness plotted against the number of invasions, this time on a logarithmic axis. Again, the gray represents the average local species richness, which reaches some asymptote, and then the regional diversity, the metacommunity diversity, converges at some time later. In the right-hand figure, I'm showing the spatial beta diversity, right? The intrinsic spatial beta diversity of this metacommunity, which initially increases, okay, in accordance with this regionalization process, right? That range size collapse that I showed earlier. And in the gray curve, this is the temporal turnover rate, okay, which is effectively zero until the moment indicated by this dashed line at which the local communities become saturated on average. So there is a clear link then between local regulation of biodiversity and the emergence of this autonomous turnover. Okay, this is numerical evidence. We also have analytic evidence, which demonstrates a link between local ecological limits and the emergence of autonomous turnover. Okay, so then let's compare the temporal signatures of this autonomous turnover to empirical observations. Okay, and again, we find qualitative agreements. On the top row here, I'm showing empirical observations, and on the lower row, these are outcomes from analysis of the simulations. So in the first row now, we have the distribution of temporal occupancy. So for a species to have a temporal occupancy of 1, it must be present at the local site scale at all times within the time series. Okay, and empirically, it's common to find a bimodal distribution in the temporal occupancy, and likewise we find bimodality in the simulations. Although note that the relative size of these peaks does depend on parameters. Then again, we have an empirical observation, species richness over time, intrinsically regulated. Here we show that even in the case of this autonomous turnover, local community composition is intrinsically regulated, local community richness. And then these last 4 panels represent the species time area relation. Okay, this is a rather subtle pattern, but it describes the interrelated exponents of the accumulation of species in time and the accumulation of species in area, okay, which together, that interrelated exponents of those patterns are described as the STAR. And again, we find a similar interrelated pattern between the exponents of the accumulation of diversity in time and space in our simulations. Okay, and finally, these are 4 different representations of autonomous turnover. In the top left, you see the biomass fluctuations. The red curves here represent the local biomass of a single species in 3 different sites. And you can see that it fluctuates through multiple orders of magnitude. The blue curve represents the metapopulation fluctuations, summing those local biomasses across the landscape. And the black line represents the metacommunity biomass, which is essentially time invariant. Okay, so if you were to go into this landscape and survey one of these sites, you might find something that looks a bit like this then. So this figure represents the observed abundance of marine fishes in the Bristol Channel. And clearly you can see that from one year to the next, these populations can vary by multiple orders of magnitude. Okay, so in this panel here, I'm showing how these population fluctuations can lead to a decay in compositional similarity, in other words, compositional turnover at the local scale. But critically, due to this intrinsic regulation, despite these multiple orders of magnitude fluctuations at the population scale, it's impossible to detect fluctuations at the regional scale with respect to the distribution of biomasses. This figure here shows the relative rank abundance curve, the time average relative rank abundance curve, plotted independently of species identity. Okay, so it just shows that the species with rank 100, irrespective of the fact that the identity of that species changes with time, will have a relative biomass that is effectively time invariant. Okay, and this intrinsic constraint on the distribution of abundances, despite these orders of magnitude fluctuations at the species scale, is also observed for this estuarine fish assemblage. Okay, so let me just quickly summarize what I've discussed and try to give a few key takeaways. First, I went over the regulatory effect of structural instability in ecological models. And through this discussion, we see the potential for structural instability and its opposite, robust coexistence, not just in determining the outcome of extreme abiotic or biotic scenarios, but as a fundamental driver of the diversity structure of these communities. Then I briefly went over the kinds of empirical evidence available of some intrinsic regulation in diversity, a process which remains poorly understood empirically. I gave you an introduction to the simple bottom-up approach we've developed for modeling meta-communities, the Lotka-Volterra meta-community model. And then I discussed the emergence of intrinsic diversity regulation at multiple spatial scales in the model meta-communities, both the local and the regional. And I showed that if you apply tests to the appropriately scaled interaction matrix, one that is sensitive to the internal structure of the meta-community, then some of the macroscopic features of those spatially structured models can be understood by making a zero-dimensional approximation. Okay. Then I went over some of the emergent, self-organized macroecological properties of these meta-communities, specifically those that by definition are not predicted by the zero-dimensional analysis. And I showed how the structurally unstable meta-community state brings with it a suite of emergent properties that match empirical observation. And so finally then, I would conclude by saying that based on this analysis, this coincident emergence of empirically realistic macroecology and structurally unstable diversity regulation. So this evidence can be seen as indirect evidence of the importance of this process in structuring ecological communities in nature. Okay, so let me just say thank you again for the invitation. Thank you for listening. Thank you to my collaborators, and please go ahead, any questions you might have.
Thank you so much, Jakub. This was a very nice talk. And if there is any questions, please raise your hand in the participant list and I shall call upon you. So let's see, are there any questions? Yes, Bob Holt.
Yes, hi. That was really a lovely talk. Wonderful work. Sorry, I'll see if I can get my face to show. Okay. I have several observations and questions. One is something you may have touched on right at the end, and I apologize if I missed it, but another macroecological pattern you could look at with the model that people have thought about a long time is you talked about the range size distribution earlier, but there's also a range abundance distribution. So species that on average are abundant where you find them tend to have large geographic ranges, for instance. It's not a universal rule, but it's a relatively widespread pattern, and that's something you could definitely look at in your meta-community model and see what it says, when it holds, when it doesn't hold, and so forth. So that's a suggestion, really, of something you could do. Another is you never use the word saturation, which of course there's a big literature and big debate about whether or not local communities are saturated or unsaturated in species. And empirically, the question is still open. I mean, in invasion biology, there are a lot of examples of invasive species coming in and nothing obviously happens to the native community. We tend to focus on those species that have a dramatic impact. The great majority of invasive species come in and they're just added to the local community without any obvious impact. And people have argued that that's evidence for kind of generic unsaturation of local communities. And then when you see saturation, the sort of leveling off of species richness, there are two basic explanations for it. One is that you have continual turnover in the McArthur and Wilson sense of colonization matching local extinction. In your case, the extinctions are driven by local dynamics. And the other is a set of species colonize and then exclude newcomers, right? So you have a resident core of the community and things come in, hang around for a while, but they get to be excluded. And those are two very different views of the world, I think. You have a constant churning in the whole community, or you have a subset of the community that's always there, and kind of it keeps most newcomers out, kind of on average, much of the time. And that's something you might look at in your models as well. Okay. And then two other final thoughts. This is an invasion analysis, and that always requires saying something about the species pool, where are the invaders coming from, and making different assumptions about the nature of the species pool could have consequences for what you see. And if you get large enough spatial scale, say Madagascar or Australia, what you're seeing is there's very little colonization from outside. There's no species pool you're drawing it from. You've got in situ evolutionary processes of diversification. You might ask yourself a question whether or not the same phenomena occur when the new species always come about because of a small deviation in their phenotype from a pre-existing species, okay, as an evolutionary assembly process versus an ecological process. And then the final methodological thing I'd be interested in is you've got dispersal in your model, right? And of course, dispersal can go from 0, where you still have stuff coming in from the outside, raining from heaven, and then you're filling up a heterogeneous landscape, which is kind of dull maybe, or you have complete mixing. And if you have complete mixing in a Lotka-Volterra world, you've just got some kind of average interaction coefficient. And then you have lower rates of dispersal. So it'd be interesting to look at what happens as you go from almost 0 dispersal to complete mixing. Are there sort of interesting, unique things that happen in between? I mean, there's things like source sink phenomena and so forth that I would expect to show up pretty commonly with moderate rates, but not too high rates of dispersal. So those are just some comments I had, and it was really great work. And I look forward to reading some of your papers that I've missed.
Great. Well, thank you very much. So yeah, there's a lot there. Let me just comment on some of the points, because we have looked at some of these ideas. So what you call the range abundance distribution, I have looked at this, and there is indeed correlation between the average biomass of a given species at the local scale and its regional range size. Okay, so we do see some of that range abundance distribution that you're talking about. So in empirical systems, of course, you would expect there to be some distribution along a specialist to generalist gradient, right? So you could, in the case of an extreme specialist, you could have a high local abundance, but then a low regional site occupancy. And our models exclude that at the moment, at least. But despite that, we still see that kind of correlation between the average local abundance and the site occupancy at the regional scale. You talk about varying dispersal, and we of course do a lot of experimentation with varying the dispersal length within the system. In some contexts, we're able to reproduce previous results in which if you have extremely high dispersal, you end up effectively with either a monoculture if there's very high interaction strengths, or a single community at all points in space, which effectively just verifies that assumption that in the high dispersal limit, you converge back from the metacommunity case into a single point community case. So that helps to confirm at least that the dispersal processes operate as expected. I would say though that in the real world, right, we might expect dispersal to operate somewhat differently. We might expect dispersal to be a stochastic process, right? So in the way that we've modeled it in this simulation, it's a deterministic process. There's this constant rain from heaven, as you say, of propagules from one site to the next. In reality, it's probably more like a case in which every now and then, stochastically, some propagules of a species will arrive at a given site. And it's not totally clear how that modification might change the emergent properties of the metacommunities. My feeling is that the reality is probably a mix of these two things, right? There's probably, to a reasonable approximation, some species and some sites are constantly exchanging propagules, constantly exchanging biomass, whereas some species, their dispersal process is more like the stochastic case. So it will be interesting to try and look at how that addition of stochastic dispersal might change the emergent properties. On the species pool assumption, it's very true that we assume effectively an infinite species pool. Okay, so at each iteration, we randomly generate a novel species with no constraints whatsoever on its ecological traits. Okay, so it's sampled from an infinite pool. And although we haven't looked at this, there are previous results that show that the size of that fundamental pool can change the outcomes of your models. Okay, so we only assume the infinite case. In other words, we assume a sufficiently large system that any new species is effectively novel to the meta-community. But yes, so adding some kind of adaptive dynamics would certainly be interesting, although I'm not sure that we're quite finished with the ecological analysis yet. But yeah, thank you very much for those points.
Thank you so much. Giza was the next. Please go ahead.
So Jacob, is very, very interesting, and I want to ask you to remind me about the basic things. How did you define the local matrix, and what was the difference between the patches? And I will be interested in the interaction between these two issues.
Okay, so the local matrix is defined by simply randomly generating its elements, randomly sampling its interspecific interaction coefficients from some
But you also had a slide with some niche segregations. This one
here. Yep.
Yes. What is the relation between this and that?
So this is another simplifying assumption that we apply in the system. We assume that the interspecific interaction coefficients are independent of environmental preference. Okay, so we have no competition kernel. This is a simplification. Here we have, so there's an underlying abiotic distribution and then an environmental response function, which defines a species growth rate in space. Okay, and each species is allocated a randomly generated environmental optimum, which defines their preferred abiotic conditions.
Oh, yeah. You mean, okay. So it is not an issue in the interaction sense, okay.
Yeah.
And what was the difference between the patches?
So the patches at each site in space, let me go back to this network here. Each site is allocated a unique environmental variable. Okay, so the color here represents the distribution in a given environmental variable over space. Okay.
Yes, and how it will affect the species?
Through the environmental response function, each species has a unique environmental preference and a unique value of that environmental variable at which its growth rate is maximum.
Okay, so the species has some places are better for written than another one.
Exactly, yes.
And then,
okay, go ahead.
Okay, then you said some things that the local diversity determines the diversity of the metapopulations, but I also can assume that the segregation between the different kind of patches also is a kind of equal factor of maintaining species diversity.
Yes, that's absolutely the case. So like effectively that spatial niche segregation, right? That difference in environmental preference leads to the spatial isolation of two species, yes, which might have a non-zero interaction coefficient, but because they don't meet in space, their effective interaction coefficient at the regional scale can be approximately or precisely zero, and so it can be seen as a coexistence mechanism for sure.
Thank you.
So, yeah. Okay.
Thank you so much. Miguel Rodriguez, you're next. Please go ahead.
Thank you. Really fantastic framework, Jacob. Very fertile approach. I wanted to ask about, so there is this old idea, I believe going back to John Lawton and Diane Srivastava's work, that there are the systems kind of segregating type 1 system that is driven primarily by regional species pool, where most species have a dense occupancy, versus type 2 systems where we have
high patchiness. I lost you for a second there. Could you repeat that question?
Yes. So I was saying there is this idea of type 1 systems where there is dense occupancy in the species range for most species, versus type 2 systems that are driven by local dynamics, but local factors like species interactions, where we have very high patchiness. And I believe some of that, I saw some of that in your CAR dynamics and the linear correlations with the W parameter. But is that expectation, well, first of all, is that expectation generally captured by your approach? And second, could we use this framework to do this reverse ecology trick of trying to measure patchiness and feedback that into estimating the relative effect of regional species pool versus local factors.
So just so I understand, the type 1 and the type 2 case is that one. So type 1 is to a reasonable approximation a well mixed community, and type 2 a spatially structured one.
Yes, but with the specific expectation that there is high patchiness within the species range.
Okay.
Because you could also have small ranges that are densely occupied.
Okay.
Right.
And densely occupied and essentially monocultural, you know.
Right.
So without interactions. Yeah, I see what you mean.
Right. Exactly.
Okay. So the difference then is between effectively patchiness driven by interactions at the local scale and patchiness driven by abiotic filtering, for example, where you have a very dense and essentially so monoculture at the local patch scale. Is that I may not fully understand.
So type 1 will be driven by the regional species pool. So I know in your model you have this infinite species pool, but the total size of the regional species pool is somewhat it saturates, even if the actual identity.
So we have if you like, an infinite global pool and then
exactly.
a finite and defined regional pool.
Right.
Yeah.
Right. So that will be the main constraint in a type 1 system in which basically the factors, the abiotic factors of the entire region is mainly driving this distribution, whereas in a type 2 is local factors that are primarily driving the distribution, either through species interactions or.
Okay. So I think maybe we should. Could you write to me about this and we could discuss it in a written way rather than, because I don't fully grasp how you could apply that to this system. But yeah, thank you.
Yeah, but this slide is actually what.
Okay.
Yes.
So in this slide, just to give a little bit more interpretation now that we have a bit more time, the blue color here represents the narrowest abiotic niche width, and the red color the widest abiotic niche width. Okay, so the way that I interpret this figure is that when the abiotic niche widths are extremely narrow, right, species are extremely filtered by the environment. Essentially, their ranges are largely insensitive to the total landscape area, right? Because they already have very narrow spatial ranges as a result of that strong environmental filtering. So if you increase the total area of the system, then the average interaction strengths are not so strongly affected. Hence, we have a shallower exponent for this competition area relation. In contrast, when the niches are very wide, species interaction coefficients are much more sensitive to increases in total area. Okay, because ranges can conceivably occupy much, if not all, of the landscape. So I thought I'd just go through a bit more of additional interpretation of that figure now that we're on it. Yeah.
Thank you.
Thank you so much. Yeah, Axel, please go ahead.
Thank you. So in the things that Bob Holt says, there was one slight point of criticism which I wanted to respond to because it's fundamental. He said when we look at species invading a community, we don't see other species going extinct. And you might say, oh, so therefore maybe this whole idea of saturation is not true. But we have looked at this. And the first thing that people may have missed is that the species that usually goes extinct is one of the rarest species in the community, and you simply may miss that it goes extinct. The second thing is that it is rare and its population dynamics is slow, and the extinction will be much, much slower than the invasion. And you can even work this out, and you find that the time scale of extinction is a square root of S longer than the time scale of the invasion. So therefore, if you say, oh, we see a species invading and essentially nothing happened in response, that's exactly what our theory predicts. And still you have saturated communities.
Thanks. Bob, did you want to say something to that?
Sure.
Yes.
That wasn't meant as a criticism. It was meant as an observation of what you would find in the literature. I think what you ought to do is write a paper that's addressed to invasion biologists that makes that point. I think that's a really valuable point. The time scale of extinction is really important here. Like what's the time scale over which you're measuring the instability of the community, right? I mean, the idea of a saturated community, there's actually, you introduce the invader and instantaneously nothing happens, but over some time scale, there's competitive exclusion in your model, Lotka-Volterra model. And so the initial community, it's got your kind of edge of stability criterion, but it's the same set of species pushing out the new invaders when they show up, right? Anyway, it'd just be an interesting exercise to try to actually relate what you're doing to things that empirical invasion biologists can grapple with, because this has been a big debate. Dov Sachs and Jim Brown, people like that, have written papers saying that, well, you look around the world, invasive species come in, and you don't see extinctions, so it's not really a problem. But it may be the time scale of extinction is just longer than we've had to look. Maybe centuries, millennia. It may not be 5 years or whatever, right? I mean, I think that's an important point for applied ecology.
Okay, thank you.
Yes, thanks very much. Are there any other questions? Oh, Rafa, yes, please go ahead.
Yeah, just a point of clarification. I want to understand about this point of the number of species being constant in time, being compatible with either low turnover or high turnover. There was a slide that showed some empirical data where there were 3 curves, right? The number of species, but also the number of introductions and the number of losses. Wasn't that the case? And we saw that there were introductions and losses. It was just that the net result was the number of species was relatively constant. Yeah, that slide.
Yeah.
So wouldn't that be evidence against the idea that you have a core community that is resistant to invasions and consistent with the idea that you have turnover and you add new species and lose old species?
Yeah, I mean, it could be the case that most of that turnover is focused amongst a small subset of the community. I haven't seen there isn't any more data available from this paper, but that is my assumption, yes, that there is a continuous turnover in composition within these sites. And that's also indicated by the slope of this Jacquard similarity with the function of time, right? So let's assume that the authors have a reasonably long time series. If you basically are just exchanging a handful, a subset of the community, some taxa coming in and out, then you would probably detect no trend in the Jacquard similarity, but they do detect a significant negative trend over time, suggesting continuous turnover in composition.
Yeah, thank you very much. Oh yes, Bob, please go ahead.
Very quick point. I think this varies from system to system. I remember work that Mark Williamson reported in his island population book some years ago, and it was this 40-hectare woodland in East Anglia in England, where these local ornithologists had gone out and census birds for during World War II up to the present. And there is turnover. There's constant turnover, and you would have graphs that, just like the one you saw. But if you looked at actually which species were there, you track species over time. There's a subset of the community, the great tit, the jay, the chough or whatever. Well, it wouldn't be the chough in East Anglia, the rook maybe. Some species were always there, and then there were a lot of rare species that came and went. Okay, so that's an empirical question, and that's perfectly compatible with the graphs you just showed. And it'd be interesting to see if something shows. You can look at your model like that, right? Where's the turnover occurring as a function of, say, local average abundance in species, right? Is it mainly the rare species in the community, or does it also include common species? They're common for a while, but then wham, they get knocked out by something that colonizes and excludes them from the community, something like that. That's something you look at in the model, be very cool.
Yeah.
Yes. Sorry, Jacob, did you want to say something to that?
So I think that like it is the case in the model that we see some correlation between the lifetime occupancy of a given species and its maximum biomass, right? So the species that are typically rare, they exist within a given site for a shorter time than the species that are common. But I don't have a complete picture of of what that relationship is like. So the local abundance and the local persistence in time.
Thanks. By the way, in the meantime, there was another question from Miguel in the chat. If there is time for an additional question, have you studied the consequences of using a species distribution of W, modeling specialist to generalist ranges instead of one global constant parameter?
Yes, and I'm very curious to know what that would be. But the thing is that I don't understand empirically what that distribution might look like. Okay, if you go into nature and you sample a bunch of individuals from different species, you bring them back to the laboratory and you put them through a load of experiments, what is the distribution in the abiotic niche width of that community, right? Are most species generalist or are most species specialist? I don't know what that distribution would look like, and I'm also not sure if you could test that empirically, right? Because these niches are highly multidimensional. So you could ask what the abiotic niche width of a given subset of your community is in temperature space, but then you ignore the complex multi-dimensionality of that niche width. So if I knew what that distribution might look like in nature, then I would be very tempted to try that experiment. But because I don't know how well understood that would be, I haven't done so yet. So for simplicity, we keep that niche width fixed for all species. But yes, it would certainly be interesting.
Thank you. Giza, please go ahead.
Okay, so my last question is whether why do you need an external species pool? But it would be possible to assume that the species pool is maintained by the metacommunity as a whole, which is a species pool for the local communities.
And you mean to sort of initiate your model with some set of species pre-present?
Yeah, so generate some adaptive dynamics or something. So
sure.
And then the metacommunity selects the species which can maintain themselves on the metacommunity level. And
yeah. I mean, I think it's largely a sort of a methodological choice, right? We choose to assemble in a stepwise way so the system essentially self-organizes, and we can observe along that assembly gradient, which can be to just spontaneously introduce large numbers of species and allow it to effectively prune itself down to some emergent distribution.
Thank you very much. Are there any other questions? It's very, very late, but if I actually did have one more question. I'll try to be very quick about it. Do you have anything to give intuition as for why in the meta-community case, the spectra of the matrices shrink the way they do? And I'm thinking in particular, there was a paper not too long ago by Dominique Ravel, which did something similar, where they had a spatial model and they had this kind of effect of shrinking the spectrum and therefore stabilizing dynamics in a spatial context. Is this analogous at all, or is it, yeah, exactly, that's the one.
I think so. Yes, I got a bit mixed up when I was explaining it, so I didn't do a very good job. So basically, at the regional scale, of course, we get this self-organized isolation of populations, right? So they can distribute according to their environmental preference or as a result of biotic repulsion, such that they don't actually interact, right? So when we compute this regional interaction matrix using this harvesting experiment, we take into account the fact that they may not co-occur in space, okay? And in that context then, the estimated coefficients describing the interaction between two species is likely to be less than that at the local scale if they were to co-occur. And so you get this a general decrease in the interaction coefficients and an associated shrinking in the spectrum of the regional interaction matrix.
So that would mean that it's probably a completely general phenomenon.
That if you increase the spatial scale and
Exactly.
heterogeneity and then try to estimate your interaction coefficients, yes, I would assume that it would be general, that you would get a decay in the effective interactions.
Okay. Thank you so much.
That's okay.
Any last takers? Yes, Rafa, please go ahead.
Yeah, sorry for keeping things going for so long, but like you just mentioned, generalities, and one of the things that struck me was that your model is very much non-neutral, right? Species differ by their environmental preferences, and the matrix has positive, negative terms. Species are very much not ecologically equivalent. But then you find that the species rank distribution is independent of species tags, right? It's unrelated to ID of the species. So that got me thinking, if you were to set all of the interactions to 1, right? So you make your species equivalent, like what of your results will be different, of the range distribution, all the distributions that you looked at, how many of them are sensitive to those, to ecological differences between species, and which ones are not?
Yeah. So in lieu of a kind of complete analytic theory that explains the relationships between the local process and in the emergent properties, which we currently don't have, right? I can't really understand completely the parameter dependence of these various emergent properties. Okay, but in my experience working with the numerical system, if, for example, you have a perfectly uniform environment, then the same properties will emerge, but at a larger scale. Okay, so let's say you've got an environment of arbitrarily, let's say 20 sites. If the environment is uniform, then you might get the identical community at each site. But the same model with 2,000 sites, and you're going to start to get some spatial structure as a result of biotic interactions alone. And that spatial structure will eventually resolve the analogous macroecology that I just described. Okay, again, because we don't have the analytic theory, I can't say that with 100% confidence, but my experience is that within that parameter range or that parameter combination that actually gives you some internal structure, the emergent properties are robust to variation in these model parameters.
Thank you so much. Are there any other questions? If not, then thank you so much again for the very nice talk. And thank you everybody for attending. We shall resume in 2 weeks' time. And I believe Giza or Chris will know who the next presenter is. I don't have it off the top of my head.
Chris, do you have the slide?
I can tell you that it's Matthew Leibold.
Okay, thank you. Excellent. So in 2 weeks, Matthew Leibold is going to come and give a talk here. So we hope to see you all here again. So thank you again very much for the talk and for coming, and see you next time, and have an excellent rest of your day, evening, whatever that may be for you. Bye, everyone.
Bye.